Well, this is the 10th presentation on structure and properties of organic molecules, and we're on our last task, seeing stereochemistry. We started by learning just how to draw valid structures for carbons, nitrogens, oxygens, hydrogens, and moved quickly to seeing beyond those drawings orbitals and where electrons sit in space in terms of orbitals. We looked at partial charges for neutral structures, or where positive and negative charges in cations and anions would be delocalized or spread to through resonance. And again, that was just a structure, not a dynamic transition between resonance forms, but a spreading out, a delocalization of charge to create partial charges at different places. So that was hard. But we went through that, and we looked at then how acids might react with a neutral molecule, as this may act as a base in acid conditions, or if taking the solution and making it basic, that this neutral molecule is, or whatever neutral molecule is put into, where would we propose acidic protons to be if this was added to a base. So we looked at acidic and basic sites within neutral molecules. Then we moved a little bit out of the depths of structural analysis into maybe some easier concepts where you look at just the rotation around bonds. Carbon-carbon bonds were the focus. We might take an alkane and look at different conformations through Newman projections and chair conformations. We're now on our last box, the 6th task, seeing stereochemistry. And really there's a connection between these two boxes. When we have conformations or orientations in space that are sort of locked in to the structure, it's part of the structure, we call that stereochemistry. So conformations or orientations that are locked in, we call that stereochemistry. It's a very important part of our world. Our bodies rely on molecules not only having a certain constitution where things are bonded, but very much rely on having the atoms bonded to that carbon or place in the right way, in the right orientation. So things that are bonded not just to a particular site, but to that particular site in a particular way. So we talk about sort of where they're bonded. I'm just going to talk about regiochemistry a little bit, but we also talk about stereochemistry of reactions, of compounds. These are very important terms, the regiochemistry of a molecule and the stereochemistry of a molecule. So we have 3 videos left, or presentations, 10, 11, 12, and the first one in unpacking this box on stereochemistry is just going to look at what is a chiral molecule, how do we find it. The second one is going to look more at how do we designate it, not by optical activity, because chiral molecules are optically active, but what is the absolute configuration, R and S, Kohn-Ingold Prelog notation, what is the fitting descriptor, stereochemical descriptor, R and S, for a particular atom or source of chirality in a molecule. Then the last video we'll just look at relationships, determining number of stereoisomers for a particular molecule and relationships between different molecules that are stereoisomers. So let's go ahead and look at, just real quickly, sort of a view ahead to where we're going, because this is going to be important that we understand where stereochemistry, task 6, really fits into the world of organic chemistry. It really fits in more as we look ahead towards reactions. Understanding that we're going to take molecules that we can now see better. I know now we see beyond just letters and lines. We could see a partial charge here on this carbon due to an inductive effect of bromine. This is all well and good. We know each carbon is sp3 hybridized. This is something, again, our eye can see, but we want to know as we go forward into the next 12 presentations, beyond just seeing structure and properties of organic molecules, we want to know how things react. So Let me just tag sodium with a full positive because it's bonded to something other than itself, and they usually then give up their electrons. But this is the key. We want to know for reactions not only where this carbon that's full negative, that's most reactive, is going to attack, but we also want to know how it bonds to a particular carbon. So I'm going to go ahead and show an arrow. This is again just really looking ahead towards the future. We would say, hey, negatives like positives. So this is going to make sense. Where we attack, where we put the cyanide is here. That's a regiochemical question. Where is it going to attack? What carbon is it going to attack? Well, it's going to attack the one that's partially positive because it's full negative. And we're going to break away the bromine as bromide. And again, this is a little bit ahead of where we are right now, but it's sort of just illustrating the importance of stereochemistry. Now you notice what I didn't do is I didn't show its orientation. See how we went from bromine on the wedge to just having cyanide come in where? To that carbon, and shown with just a line showing it's bonded where? Right here, but no stereochemical information. Well, most reactions have some sort of stereochemical descriptor. It may be that you don't have selectivity towards a particular stereochemistry, or it may be that you do have selectivity towards a particular stereochemistry. In this particular reaction, we need to draw it more accurately or more precisely to say it's not enough just to say where cyanide bonds. I'm just having a little fun. They usually are drawing these reaction arrows straight across, but we're showing it as coming down. So we do again the same thing, but what was lost up here we're going to add. Where it bonds, that's been set by partial charges. But how does it bond? Is it undefined? Is it not select? No. In this particular reaction, this is called an SN2 reaction. We're going to unpack that later. In SN2 reactions, there are both regiochemical and stereochemical descriptors that fit SN2 reactions that tells us not only the cyanide bonds where, right here, but it also comes in how, what they say, from the back, from where the leaving group back relative or on the other side of what is the leaving group. They call it inversion. So it bonds not only to a particular position, that was regiochemistry, but stereochemically it bonds to this in this way such that it's on the dash because the bromine was on the wedge, and we have to have an inversion. The term inversion is a stereochemical descriptor for the SN2 reaction. So this would be our product in its full detail, not just this. Again, just reactions have those two sort of descriptors. What's the regiochemistry of a reaction, and what is the stereochemistry of a reaction? So that's what you want to hang on to as you go into reactions. Where is it bonding, and how is it bonding there? So this will be in the next set of 12 videos as we sort of look ahead. Let's go ahead and just move through stereochemistry, our last three presentations here, this being the first of those three. We need to define what is a chiral object. Well, a chiral object is one that cannot be superimposed on its mirror image. So we can take just any particular object. This is not a chemistry specific term necessarily. We can look at a pen that you put papers up on the board with, and we can see that if we take a mirror image of this, let's say out front here, I'm just going to make a very bad drawing, we could put this right back and superimpose it on the pen that's shown here. But if you do that with hands, the mirror image, this is the mirror image of the little boy's or girl's hand, and this is the adult's hand, and we can see that if you try to take the mirror image and superimpose it, put it right back into and and hide it in, so to speak, the original hand on the left, it won't fit. The thumb will be on the wrong side. These are non-superimposable images or structures. These would be then chiral objects. Chiral objects also do not contain a plane or point of symmetry. This does. We could cut in many ways through the pen and have a plane of symmetry. Maybe not a point of symmetry here, but a plane of symmetry. There are many. So how do we bring this down to molecules? Well, we tend to, I guess, think of chiral objects as just those that are molecules, but we can, again, expand that beyond. But for molecules, we're looking for non-superimposable mirror images of each other. This defines, just like with our left hand to our right hand, is a very special relationship. There's only one mirror image of a chiral molecule. There's only one. And those two objects are called, we could call these hands. This doesn't really fit because this is, enantiomers is more of a term for molecules, but we could call our hands enantiomers. They are non-superimposable mirror images. Again, this is really for just molecules. So let's go ahead and draw that 2-bromobutane we started with on the last slide, and we said it was shown on the wedge. It was just shown that way, and we started with that. But we could draw the mirror image of this. So what I'm doing again is I'm holding this up to a mirror, and I'm going to draw this that's closest to the mirror will appear first, then second, and then third. The bromine's still going to be coming out. And then, of course, last in the mirror image would be our carbon here. So this would be a mirror image. But if I tried to bring this back and superimpose it, I'd have to flip it over. And the bromine, if I flip that over, will be on the dash. This may take a kit to see, but you can take this molecule and try to superimpose it on this one, and you can't. Because this bromine, if I flip the molecule over so that I at least have the constitution right, first carbon and then the second one having the bromine off of it, if I flip that over, the bromine will be on the dash. So if I take that and flip it, let's just do that. My bromine will be on the dash. So I took this one and flipped it, but it is not the same. These are different in stereochemistry. They are non-superimposable mirror images. They are enantiomers. Now we can find very quickly enantiomers for any chiral molecule by doing a little trick. I'm just going to talk about these molecules. We can see this does not have a plane or point of symmetry, this first example. And since enantiomers are monogamous, there are only pairs of enantiomers. To find the enantiomer for any chiral molecule, switch any two groups off of each chiral carbon. We're going to get to what this means. But just in general, if you have wedges and dashes within a molecule or a representation that you know is chiral, and we say, well, how do you know this one's chiral? Let's just go back to the old definition. We're going to get to the new one. What is a chiral carbon? But this does not have a plane or point of symmetry. That was one of the descriptors we can use for chiral objects. Does not contain a plane or point of symmetry. So this one does not. It's chiral. And if we then want to draw the enantiomer, that monogamous pair, we could take wedges to dashes. So we take this wedge to dash and this dash to wedge. This would be its enantiomer. Now again, this is going to be just for around chiral carbons, but it's a good trick to find the enantiomer quickly. We can do the same thing here, where we know this does not have a plane of symmetry because this side would not reflect into this side. It doesn't have a point of symmetry. This is chiral. How do we draw the enantiomer? Just take wedges. These wedges are meeting up at a carbon here at the top, to dashes, and wedge to dash and dash to wedge. So we just flip all the dashes and wedges. Now it's a little bit hard if we have this view here of a molecule where it's more of a three-dimensional look looking from the side for this bicyclic system. It's really this molecule here, just from a different perspective. If it's drawn this way, it's probably easiest just to imagine the mirror and to draw the mirror image if it's drawn the molecule from a sort of a side view instead of a top view of the cyclic structure. This would be its enantiomer. Okay. So there's just different ways to draw quickly the enantiomers. Now let's get back to, though, what is this term, chiral carbon? How can we use that to help define chirality? Because so far all we've looked for is just planes or points of symmetry. If we don't have it, that molecule is chiral. Or if it's non-superimposable on its mirror image, then it's chiral. And this would be non-superimposable on its mirror image. Let's get to this definition of chiral carbons, or what we call asymmetric carbons. We could ask for any molecule, is it superimposable on its mirror image? This would not. Is there a plane or point of symmetry? We can see this has some some asymmetry to it. There is no plane or point of symmetry. But this doesn't really hit at what is the source for this molecule of chirality, the source of chirality, the source of handedness, the source of these properties. So we ask a better question: do we have a stereocenter, or in most cases an asymmetric carbon? Well, you have to define what the asymmetric carbon is, the source. It's a carbon wherein you have an sp3 carbon bonded to 4 different groups. So we can walk through this molecule that doesn't have, I guess, a plane of point of symmetry or is not superimposable on its mirror image. That is true for this. But we can ask the better question: where's the source of that chirality? Well, it's not here, because this carbon has 3 hydrogens off of it. So it's not an asymmetric carbon. This one has 2, but this one here, it has a bromine, it has the hydrogen that's not shown, it has an ethyl group, a CH2CH3 group, and then this big whole thing. Those 4 branches are different. So we could say this is an asymmetric carbon, and I'm just going to label those with asterisks. So we have 1. But that may not be the only source for chirality here. We can have, if we have at least 1, we have a chance for enantiomers. We usually do. If we have more, though, that can give us just more sources for chirality and for stereochemistry. So let's keep walking through this. This carbon here has a hydrogen not shown, this branch to the north, this branch to the sort of south, yes, east, or to the south and to the right, and then this isopropyl group, and of course the hydrogen. So these branches off this carbon are different, along with the hydrogen, which is different. So this is a chiral center, or chiral carbon, or asymmetric carbon. This one would not be, because these 2 groups are the same. This one here, we can say these 3 groups are different. Ethyl is not the same as CH2CH2CH3, so this branch is just different from this branch by 1 CH2 group, which is different from this branch, which is also different from the hydrogen that's bonded here. So this is an asymmetric carbon. So we have 3 within this molecule. You only needed 1 to, I guess, have a chiral molecule, but this had 3. We can do the same thing with penicillin. You usually look for wedges and dashes. This would be an asymmetric carbon, this would be an asymmetric carbon, and this would be an asymmetric carbon. So in penicillin we also have 3 what we call asymmetric carbons. Now we're almost done. We want to make a association again between, between asymmetric carbons and chirality. If you have asymmetric carbons, you have a chiral molecule. Again, we only need 1. Here we had 3 and 3 for these 2 examples. There is one exception to the rule: if asymmetric carbons, then a chiral molecule. And we need to cover that and we'll be done. So the rule is, if asymmetric carbon, then chiral molecule. So we're talking about the source of chirality, and that being the asymmetric carbon, and it affects the whole molecule. So let's take trans 1-chloro-3-methyl cyclohexane. So we're going to put the chlorine at the 1 position, walk 2 steps over, 1, 2, 3, 3-methyl. Now it says trans, so this is indicating a opposite side of the ring orientation that's locked in between the chlorine and the methyl group. Now actually there's more to this story. I drew this one, but there's actually 2 ways to draw trans 1-chloro-3-methyl cyclohexane. We'll get into that more later, but this is a representation of trans 1-chloro-3-methyl cyclohexane. We could ask the question for this structure that fits this name, there's one other, does this structure have stereocenters or asymmetric carbons? I think we do. We have one here. Chlorine is different from this branch, which is different from this branch at a distance. This branch is the same looking here, but if we look here, these 2 branches are different, and of course the hydrogen. And this carbon would also be an asymmetric carbon. This branch going this way is different from this branch at the second carbon. 1, 2, this has a chlorine off of it, this doesn't. And a methyl and a hydrogen, so this would have asymmetric carbons, 2 of them, or stereocenters, and check, it is chiral. But there's an exception. Let's take cis 1,3-dichloro. Instead of a chloromethyl, let's take dichloro, and let's make it cis. Same side of the ring. This, we could say we have chirality centers still. This branch is different from this branch. If I go out 2 carbons and hit this point and then go out this branch, this side of the bonding from this carbon is different from this side when you go 2 carbons away. That's also different from the chlorine, which is different from the hydrogen. So this is a chirality center or asymmetric carbon. And so also with this, if we go the other way, we start here, we'd say this carbon does not have a chlorine off of it, this one does, so they're different branches. But in this case, though we have asymmetric carbons, we have 2 of them, it is not, or no, it is not chiral, because I can clearly see that I have a plane of symmetry. If I cut through these carbons, this would reflect over to this. So it has asymmetric centers, this is important, but it's not chiral. They give compounds that have asymmetric centers, yet is not chiral. They give that a special name. This compound is called a meso, pronounced more with a Z, not meso, meso compound. Let's look at one more example of this and we'll be done. So if we had a compound that was not defined in terms of stereochemistry, wedge or dash, we could say, hey, there are 4 ways we could consider this. Dash, dash, wedge, wedge, dash, wedge, wedge, dash. We could draw, propose structures that fit this constitution or regiochemistry. So we could propose those. Now these we could see would be the same because I could flip this over and put it right into this, superimpose it. But the question I want to sort of propose to you is this molecule that's now drawn twice, really, because they're the same, is it a meso compound? I hope you're saying yes, because I can see that it has chirality centers. We're just going to pick this one over here because these are the same. It has chirality centers, yet it has a plane of symmetry through the ring. This carbon is the asymmetric center, again having an O off of it. This branch is different from this branch, going this way compared to this way, and there's a hydrogen off of it. And the same is going to be true for this one. So it has asymmetric centers, or chiral carbons, and a plane of symmetry. These molecules are called meso compounds, and they're not, they're not enantiomers of anyone. They're not chiral. You have to be chiral to be an enantiomer of someone. So we can't just say, like we did on the slide talking about drawing enantiomers quickly, we can't just say, well, I'll just take wedges to dashes, dashes to wedges, dashes and dashes to wedges and wedges. You do that for enantiomers. Well, this we just said is a meso compound. It does not have an enantiomer, so this we don't have to draw because it'll be the same compound. So again, just know that meso compounds have asymmetric centers but are not chiral. That's it. We'll have the last two on stereochemistry, looking at R and S designations and then relationships.